In this class, we'll see what is the nature of a quadratic form. Nature, we mean what is the definiteness of the quadratic form and what are the other aspects, like index, signature, and all these things of a quadratic form. Basically, to find its definiteness and nature, we have to reduce the quadratic into its canonical form. Right? We have seen in the earlier classes, given a quadratic, we know how to represent it. It's in a matrix form. Like a Q can be represented in a matrix form as Q equal to X T A X, where X is a column matrix of variables involved in the quadratic, and A, we choose it as a symmetric matrix. And of course, X is known, X transpose, getting X transpose is a pretty simple job. Now, a quadratic can be reduced to its canonical form. By canonical form, we mean a quadratic which consists of only square terms. It can be done in two ways. One is a linear transformation, X equal to Py, where the transformation matrix P is a non-singular matrix, and another is an orthogonal transformation, X equal to Py, where P is an orthogonal matrix. Namely, we choose its columns as an orthogonal column vectors, and later we normalize that. Then AOP will become an orthogonal matrix, and X equal to Py is the transformation which transforms the given quadratic into its canonical form, Q dash. So, what's the procedure? Given a quadratic, we'll write the matrix of the quadratic Q. We choose it as a symmetric matrix, right? Then find the eigenvalues of A. Then we know that the eigenvalues will go as the coefficients in the required canonical form. Then by looking into the canonical form, we can come into a conclusion about the nature of the quadratic form and the definiteness of the quadratic form, right? If given quadratic Q is in n variables, say x1, x2, x3, and so on, xn, we change the coordinate system, then a y, we shift it from x space to a y space, then we know that a y will be in y1, y2, and so on, yn, right? So that's a pretty simple job. Sometimes some variables may die, right? One dimension may collapse, and a whole lot of things. We get an idea once we get the spectrum of the matrix A, right? So what we do, given a quadratic, we'll write its matrix, get its eigenvalues, and looking into the nature of the eigenvalues, we come into a conclusion about the nature of the quadratic, right? Right, here it is. If all the eigenvalues are greater than 0, right, then we'll say that a given quadratic is positive definite. For example, if A, the matrix of the quadratic Q, its eigenvalues are lambda equal to 2, 4, 6. We see that all of them are greater than 0. So we say that that quadratic is a positive definite. Negative definite. If all the eigenvalues are negative, that's a less than 0, strictly less than 0, then we'll say that a given quadratic is a negative definite. Example, if A is lambda equal to -2, -3, -4, then all of them are less than 0, then the quadratic, which is represented by the matrix A, then the quadratic is said to be negative definite, right? If at least one of the eigenvalue is 0 and the remaining are greater than 0, then we say that it's positive semi-definite, right? For example, lambda equal to 0 to 3. Right? One eigenvalue is 0 and the remaining or greater than 0, that's positive. So we say that it's a positive semi-definite. And if at least one of the eigenvalue is equal to 0 and the remaining eigenvalues, they are less than 0, negative, then we say that it's negative semi-definite. Example, lambda equal to 0, minus 2, minus 3. So one of the eigenvalue is 0, so the remaining is minus 2, minus 3. It doesn't mean that only one eigenvalue is 0. I stress here, at least one of the eigenvalue is 0. It can be lambda equal to 0, 0, 2. Then it's positive semi-definite. Lambda equal to 0, 0, minus 2. Then it is a negative semi-definite. Right? If some are greater than 0 or some are less than 0, then it's said to be indefinite. For example, lambda equal to 2, minus 3, minus 4. Or minus 2, minus 3, 4. Or 2, minus 3, 4. You know, some of them are less than 0, some of them are greater than 0, then it's indefinite. Right? So, as far as definiteness is concerned, there are 5 types of quadratic forms. Like positive definite, if all the lambda are greater than 0, negative definite, if all the lambda are less than 0, at least one of them is 0 and remaining all are greater than 0, then it's positive semi-definite. One of them is 0 at least, remaining or less than 0, that's negative semi-definite. Some of them are greater than 0 and some of them are less than 0, then it's said to be indefinite. This is about definiteness. Example. Right, there are two quadratics in front of us. The first one, the matrix of the quadratic cube is this A equal to, you know how to write the matrix of the quadratic. We have seen that in the earlier classes, right? Then its eigenvalues are minus 2, 3, 6. What can we say about the definiteness of this, right? Because one of them is negative, others are positive, right? So this is indefinite. Right? Second example, this is a quadratic and we know its matrix is given by this and its eigenvalues are 2, 3, 6. All of them are greater than 0. So we say that this is a positive definite quadratic. This quadratic is said to be positive definite, right? Let's take an example here. Determine the definiteness of this quadratic form q equal to this, right? Then first we have to write the matrix of the quadratic. Matrix of the quadratic is given by a 1, a 1, and a 1 and a 1. Now what we do? We know a quadratic can be written in a matrix form as x, t, a, x, where x is a column matrix of variables involved. The variables involved here are x1 and x2, and x transpose is x1, x2 along a row into matrix of the quadratic cube, which is a symmetric matrix, into x, which is a x1, x2. Right? We'll pick this quadratic, we'll pick this symmetric matrix, and we'll find its eigenvalues. Right? How to find the eigenvalues? Get the characteristic equation. Characteristic equation is given by that a minus lambda I equal to 0. Yeah, here I need to subtract lambda from the diagonal elements. Then expand this determinant. Then it's 1 minus lambda whole square minus 1, right? That is a lambda square minus 2 lambda plus 1 and a minus 1. There's a lambda square minus 2 lambda. That is a lambda into lambda minus 2 equal to 0. We'll get a lambda equal to 0 and lambda equal to 2. So at least one of the eigenvalue is 0 and other is a positive. So the eigenvalues are 2 and 0. Now What can you say about the nature of the quadratic here? At least one of them is 0 and the other is a positive. So it's a positive semi-definite, its nature, right? Its definiteness. Now, there's another example here. Another way of sensing whether it's positive definite or negative definite is you find the leading determinants, right? The leading determinant here is D1. I mean, determinant 1 is determinant of this guy, 3 is, which is 3, which is greater than 0, and the determinant of this guy is a determinant of 3 minus 1 minus 1 2, and it's 5 greater than 0. Similarly, the determinant of the other leading determinant is 18 greater than 0. All of them are greater than 0, so it's a positive definite. Right? Now we'll see the nature. Now, what is the nature of this quadratic form? Again, it depends upon the eigenvalues. We know its eigenvalues are -2, 3, and 6. Now, 3 eigenvalues are present, so the rank number of variables present, number of lambda present there. So rank of this quadratic is 3. Index is what? A number of lambda which are greater than 0, it's a 2, and number of lambda which is less than 0 is a 1 here. So index is a number of eigenvalues which are greater than 0, so its index is 2. And what is its signature? Its signature is a number of lambda which are greater than 0, and difference between number of lambda which is greater than 0 and number of lambda which is less than 0. So it's a 2 minus 1, it's a 1. So its definiteness, it's indefinite. So its rank is 3, its index is 2, its signature is 1. For example, you come to the second one here. Its eigenvalues are 2, 3, 6. Right? What is its definiteness? Positive definite. What is the rank? 3. What is the index? Number of lambda greater than 0. Its index is 3. Right? What is its signature? 3. Right? You come to this example. What is its definiteness? Positive semi-definite. Right? What is its rank? 1. What is its index? 1. What is its signature? 1. So its definiteness is, it's a positive semi-definite, and the rank is a 1, and its index is 1, its signature is also 1.